Welcome to this session. This session is the second part of the unit on electrochemistry. Definitely shorter than the first part. That's the good news for the day. You've already hopefully listened to the recording on galvanic cells and worked some AP problems from that recording as well. So this particular recording is all about electrolytic cells. And electrolytic cells are in sharp contrast to galvanic cells. We'll point out all the differences as we get started here. Electrolysis and electrolytic cells is the other half, like I said, of this unit. Electrolysis, the word itself, is basically describing the use of electricity to bring about chemical change. That means that these are not spontaneous reactions. The literal translation for the word electrolysis is to split with electricity. Electrolytic cells are, like I said, non-spontaneous. Their main purpose is used to separate out ores or plate out metals. So everything you've ever seen that's a nice shiny chrome piece of plating on a car, like a car bumper on older cars and such, or jewelry, anything that's 14 karat gold has had gold plated onto a sturdier metal, because 24 karat gold is pure gold and it's way too soft for practical uses as jewelry. Also, anything that you've ever seen that's copper. You know, we dig this stuff out of the ground. We mine for these metals. And so we have to take the ores back to the lab, and we have to separate the ore and refine the process so that we can get pure copper or any other metal that you can imagine out of the process as well. So there are some very important differences between voltaic galvanic cells and electrolytic cells. Number one is that voltaic cells are spontaneous, electrolytic cells are not, so they are forced to occur by using an electron pump or a battery or any DC power source. So you're going to see the words power source generically from time to time. So even flashlight batteries can serve as a DC source. A voltaic cell is separated into two half cells to generate electricity, while an electrolytic cell occurs in a single container. So when you are perusing advanced placement problems and you see something that has two containers that are connected by a salt bridge, then that is voltaic. But if you see only one container and both electrodes, this would also have electrodes in the containers, both electrodes are in one container, then that is going to be electrolytic. So a voltaic or galvanic cell is a battery, whereas an electrolytic cell needs a battery. Anox, meaning at the anode is where oxidation occurs, red cat, which means reduction occurs at the cathode, still apply. None of that has changed. Isn't that good news? You learned it once, you get to use it again. But, you knew that had to be coming, right? But, the polarity of the electrodes is reversed. So in this case, instead of the cathode being positive, the cathode is actually negative. So that is a big, big difference for you. So the cathode is negative. And you'll remember this using another acronym, or mnemonic device if you prefer, EPA, which stands for electrolytic process has a positive anode. So electrons, however, are still going to flow fat cat. So this is the only change. The only change is that we had to reverse the polarities of the anode and the cathode. In other words, they're plus minus charges. We also, in these processes, usually use inert electrodes, so that the electrodes themselves do not get involved in the electrolytic process. All right, so your new skill is going to be to learn to predict the products of electrolysis, but this is really easy. If there is no water present, then it's kind of a no-brainer. You can take any salt you wish. Let's use your good one. The one you like best, most likely, is NaCl. And we're going to simply split it into the elements Na and Cl, 2 gas. So I'd need a 2 there and a 2 there. But when we look at the half reactions, what we really have going on is we have that sodium ion going to the sodium metal. And that's clearly a reduction because plus 1 goes down to 0. So that occurs because we gained an electron. And then we take the chloride ion, and it goes to Cl2, hence the need for a 2 here. And what's going to take place here is that we have a loss of 2 electrons coming off. So this reduction is gain. There's my half reaction that's the reduction, and here's my half that's the oxidation. It's going from a -1 up to a 0 for the element chlorine. So that's easy enough if this is just molten. So this would be in the liquid phase, not in the solid phase, obviously. Molten means melted. So the cation will be reduced and the anion will be oxidized, and that's the end of the story. But if water's present, that's when it gets a little more complicated, because water competes in this process for oxidation and reduction. So you're going to have to figure out if the ions are reacting or if the water is reacting, but this again is super easy. If you have a 1 or 2A metal present, like my sodium chloride, instead of it being molten, instead it was in solution, then the sodium will not be reduced, which is a good thing, because if it were, it's a very exothermic reaction when the sodium metal itself reacts with the water, and so that could get really ugly. So it can actually generate enough heat that the hydrogen gas that's put off can actually burst into flames. So instead of the 1 or 2A metal being reduced, water is reduced. So you go to your handy dandy reduction potential table and you take a gander at it, and you find that reduction where it's going to have the water being reduced in the place of the sodium. So if your sodium plus ion is not being reduced, then it's going to be the H plus ion, the H plus out of the water, I should say. That's going to be going then to be reduced to hydrogen gas. If and if a polyatomic ion is present, no polyatomic ion will be oxidized in aqueous solution. Water will be oxidized instead. So you're on the lookout for 1 and 2A metal ions and polyatomic ions if you have aqueous solutions that are going to undergo electrolysis. So if we want to stick with our sodium chloride example, water has the more positive potential if we put that sodium chloride into aqueous solution. And we would expect to see that oxygen gas will be produced at the anode because it's easier to oxidize than water or chloride ion. But chloride ion is going to be the first to be oxidized because the voltage required in excess of the expected value, which is called the overvoltage, is much greater for the production of oxygen than chlorine. So chlorine would actually be produced first. The AP exam does not get into this overvoltage thing. I just need you to know it for your future college courses. So causes of overvoltage are really complex, and you'll deal with them in future courses. But basically, the underlying principle is that it's difficulties in transferring electrons from the species in the solution to the atoms on the electrode across the interface of electrode-solution interface that is troublesome. So again, you don't really have to worry about this. I'm just doing my job, making sure that you've been exposed to what you need to be exposed to so that you're successful in college. So here what we're looking at in this picture is an aqueous solution of sodium sulfate. Well, that's a double whammy. Polyatomic ion, first of all, it's an aqueous solution. That's when your antenna goes up. Ooh, aqueous solution, not molten, not melted sodium sulfate, but rather dissolved sodium sulfate. So polyatomic ion, never going to participate. Water is going to take its place. You just got to figure out which part of water. Well, sulfate is a -2, so that would be the oxygen part taking its place, the negative piece of water. And then in terms of the sodium, it's a 1A metal. So if you ever see a 1 or a 2A metal, it's not going to participate. So what's going to take its place? Well, metals are positive, so that would be the hydrogen portion of the water molecule. So again, there's no need to really memorize these reactions because they're on your reduction potential table, which you will have. But notice that one of them is going to produce H plus ions, another is going to produce hydroxide ions. So if my links work properly, I've already loaded them up, we should be able to see this in action. We're going to see an amateur video, and then we're going to see a pretty good video that's actually been done by a teacher that teaches a little more chemistry. This one is just kind of to capture your interest. So if I do this, and I take it off of pause, we should be able to see what's going on. Here is electrolysis. Note the bubbling. So water is definitely undergoing a chemical reaction. Gas production is your first clue. And so we're going to extract hydrogen and water from this. An electric current is going to pass through the water, and it's going to separate the hydrogen from the oxygen. And note that, I'm going to put this on pause for just a second. Note what's going on. Oxygen, the O2 minus, it has oxygen in a water molecule, has an oxidation state of -2. That -2 oxide ion, if we do split water into its ions, is going to be attracted to a positive charge. And in electrolytic cells, for that to happen, this has to be a positive anode. Mind you, we are connected to an external power source you don't see in this diagram. And the same reasoning applies for hydrogen. If you think about H2O, the hydrogen is positive, so it would be attracted to a negative electrode, and EPA kicks in electrolytic cells. We have a positive anode and thus a negative cathode. Carrying on. This is just connecting an iron nail onto a wire. It'd be better if these were pencil leads instead of iron nails. So the DC converter or the DC power source is simply a charger of some sort. Fill a large container with 2 bottles, and 2 bottles with water. So these are full bottles of water. Notice they're opening the cap under the surface of the water, so the water is now held in there, and we don't get any trapped air bubbles. So salt is an electrolyte, and I lost my connection. I'm so sorry. Salt is an electrolyte, and we were actually going to see the rest of that video. So let me go back. I'm going to delete this piece, and let's look at this one. Hopefully we'll see the last of it. Here we have All right, let's talk about that color change for just a minute. The color change is really occurring over here on this side where it's kind of that yellow-green because bromothymol blue is an acid-base indicator. And in basic solution or neutral solution, it remains blue, which is why you're not seeing a color change over here where the hydrogen gas is being produced, because it's also got a byproduct of hydroxide ions, which are basic. But over here is another story where the oxygen is being produced, because that's where H plus is also being formed as a product during this electrolysis reaction. And it's the H plus ions, not the oxygen molecules, that is causing this color change. So I want to be very clear about that. He's used an acid-base indicator, and the yellow that we're seeing right around the electrode, notice it's the strongest yellow-green kind of color right by the electrode itself, is actually due to the H plus ions that are being produced, not the oxygen ions themselves. Important thing to point out that he sort of glosses over. Okay, so let's go back, and we can close this down and not be bothered with that again. And we're back to where we belong. All right, so your big task is going to be to calculate, because you know it's the AP exam. Calculating is important. Calculate the electrical energy of electrolysis, and they come at you in 2 basic questions, and only 2, which is kind of nice. How much metal can you plate out? Which means I'm answering for a mass. I'm looking for a mass measured in grams. And how long would it take to plate out? Which means I'm looking for time, which is going to be measured in seconds, as will soon become apparent. In order to do these calculations, we use Faraday's law. Faraday's law simply states that the amount of substance being oxidized or reduced to each electrode during electrolysis is directly proportional to the amount of electricity that passes through the cell. This is a dimensional analysis fest. All of those skills you've acquired up to this point are going to come in really handy. And the way we get started, like I said earlier in the galvanic voltaic portion of the notes on this unit, I wish every unit we had a place to tell you where to get started. But here's where you start. If you've got an electrolysis on your hands, see the single container? That's a clue. See the power source, the battery? That's another clue. But if you have an electrolysis problem on your hands, then start with number of coulombs equals it, and figure out which of those three things you do not know so that you can go in search of it. So let's just be real clear on the way the units work in this, since dimensional analysis is going to be your friend. You can substitute the fact that 1 volt is really equal to a joule per coulomb. So you can do that with a joule per coulomb. 1 amp, which is how we measure current, remembering that current is a rate of flow. If we talk about a water current being strong, it's got a whole lot of water molecules passing a given point at one time and can cause a lot of damage. If we talk about an electric current, it's not water molecules that are passing by a given point in a certain amount of time, but rather it's electron flow. So instead of water molecule flow, it's electron flow. So the charge on electrons or anything else, charge in general, is measured in coulombs. So this is a coulomb per second. And it's actually symbolized by the letter I. I realize there is no I in the word current, nor is there an I in the word amp. But amp is named amp in honor of Ampere, the scientist's name that discovered a lot of this and dealt with a lot of this and figured all this out. And I really stands for inductance. Think induce. I'm certain at this point in your life that many of you are guilty of inducing behavior in another human being, whether it was good behavior or evil behavior. I'm sure you've done that. So we can take a magnet and we can induce an electric current, and vice versa. An electric current flowing by can induce a magnetic field. And so it's all related to Faraday and Ampere's work, and so the I stands for inductance. That's where the symbol comes from. But for your purposes, it's really the current, which is measured in the unit of amp, which is actually a coulomb per second. So you can play substitution games in your dimensional analysis with that. And then there is a constant in your life called the Faraday. As mentioned earlier, the AP exam uses 96,500. So this is our pretty F that you often see in print that we had seen in the galvanic voltaic recordings. So this is the number of coulombs, 96,500 coulombs per mole of electrons. So when you get stumped in these dimensional analysis moments and you need to get away from electrons and into like mass of copper or mass of silver or mass of whoever, this is your bridge to make that happen. That you can get from moles of electrons to moles of the substance based on this, as well as N, which is the number of electrons you've been crossing off in your balanced redox equations. So that balanced redox equation gives you N number of moles of electrons per mole of substance. Go consider that your bridge. And then the molar mass, or the formula weight, gives grams per mole. So we can work our way out of a lot of trouble with this. So let's try this, and let's see how we do with a fairly simple introductory sort of problem. You are going to want your reduction potential table handy, ready to go if you need it. Also the periodic tables, so you're going to want to have both of those out. So I'll wait. You can pause me. You can pause me while we work on that. All right, so we're off to the races. How long? That's code for time. What is T? What is time? And I remind you, it's going to be measured in seconds. So how long must a current of 5 amps, okay, there's my I, be applied to a solution of Ag+, important to note because I may need a molar mass of silver, to produce 10.5 grams of silver metal? Okay, so that's my mass. So what I really want to do, again, to get started when you're confused about where do I even start this, if they start talking to you about currents and amps and time, you're in the land of electrolysis. And you should always start with number of coulombs equals it. And I should point out on the formula sheet for AP Chemistry, it's going to be Q equals IT, where Q is quantity of charge. But that's too easy to confuse with Q equals MC delta T, which is all about thermo and quantity of heat. So I actually prefer to say number of coulombs equals it. But if you see it on, if you panic and need it on the formula sheet, Q is quantity of charge. And all the variables are defined on the formula sheet, so it shouldn't be confusing. So what am I looking for? I'm looking for time. So I'm going to isolate time. So time is number of coulombs over the current, which is symbolized by I. So I know I, but I need the number of coulombs. Because I know that the I is 5.00 amps, which is a coulomb per second, which is how I'm going to end up getting seconds out of this to begin with. All right, so I'm going to take a little aside so that I can get those number of coulombs. And I'm going to start with the mass that they gave me, because mass can get me to moles. Moles can get me to moles of electrons. Moles of electrons can get me to Faraday's constants, which will get me to coulombs. So I'm going to start by saying, all right, you gave me 10.5 grams of silver metal. So that's silver 0. And I look on the handy-dandy periodic table, and I find that the molar mass, because when in doubt, find the number of moles of something, anything, anytime you want to get started in a chemistry problem. So it's going to be 107.87 grams of silver per mole. Gives me moles. So 10.5 divided by 107.87 equals I knew it was less than 0.0973. I'm just going to leave all that in my calculator, but I'll write down 3 sig figs for good measure. Moles of silver. Therefore, 0.0973 moles of electrons are needed. How come? Because this is going to be silver ion. See that +1? I only need to transfer 1 mole of electron for every mole of silver atom. If it had been a +2 ion, I would need 2 moles of electrons, and I would double that number. If it were aluminum, I would need 3 moles, and I would triple that number. But this is a 1-to-1 ratio. So for every mole of silver, I need that many exact same amount of moles of electrons. And there are 96,500 moles, or I'm sorry, coulombs per 1 mole of electrons. So that cancels off nicely. And that ends up being times alpha F. We stored that earlier in a previous recording. For Faraday's constant, I'm just trying to find the F. It's above the cosine. And I get 93.25. 93.25 coulombs. And that's what I needed to sub in up here. So 93.5 coulombs over 5.00 coulombs per second is going to give me the time that I seek in seconds. So I simply divide this by 5. And I come out with 1878 seconds. And when I divide that by 60, I can report it in minutes, right? Because there's 60 seconds per minute. And I come out with 31.3 minutes. All right, so let's recap, because you've never seen anything like this before. I'm going to minimize my calculator and maximize my screen. Where did I start? I always start here. Start here. Number of coulombs equals it. What am I solving for? How long? I'm solving for time. So I rearrange and say time equals number of coulombs over I. I don't know the number of coulombs, but I do know I because they told me that I was 5 amps. So I'm going in search of the number of coulombs, knowing that Faraday is my friend. And so I take the mass that they gave me and go to moles of silver. Realize that there's a 1 mole of electrons for every mole of silver, so I could put 1 mole of Ag down here for the dimensional analysis purists among you. And I'm going to get rid of my moles of electrons, so I'll have 96,500 coulombs per mole of silver. And I end up then plugging that back into my number of coulombs equals it, now that I know that how many coulombs there are. Divide it by the 5 for my amps, and coulombs per second is an amp. And I come out with 1878 seconds, which it's good form to go ahead and put that into minutes, because that's a lot of seconds. But we would take the answer either way on the AP exam and be proud of you for getting there. So these are easy, these are straightforward, but you may need just a little bit of practice. And we're going to do a whole file in a few minutes on just being able to work the AP problems that involve electrolytic cells. So we'll go through the AP worksheet that you have. All right, an acidic solution contains the ions of Ce4+, VO2+, and Fe3+. Using the EO values listed in table 17.1, and that was in the Zoomdal book, but it's also in this particular set of notes. Then give the order of the oxidizing ability of these species and predict which one will be reduced at the cathode of an electrolytic cell at the lowest voltage. All right, so if I go, don't watch, this will make you dizzy. Close your eyes. I'll tell you when I get there. If we go back up to this table, this is table 17.1, and we've marked on it before for other things that we've needed, so I'll use blue for these. I'm looking for the Ce+4 ion. It's in here somewhere. There it is. Took me a while, but I found it. Okay, so it's right here. And then I need the VO2+ ion. I saw it in my first pass. There it is. And I need the iron 3 ion, which is right here. All right, so I'm comparing these 3 ions. Let me reread the question to you. We are looking for giving these in the order of oxidizing ability. Well, oxidizing ability is code for most likely to be reduced. So they simply go in order from high to low, which is the order that they're listed on this table to begin with this being the most positive, this being the next most positive, and this being the next most positive. So most likely to be reduced would be this, followed by this, followed by this, which is code for order of oxidizing ability, because that which is reduced is the oxidizing agent. So we simply, again, look up those values. So to recap, for Ce4+ ion, it was 1.70 volts. These were all positive. For the VO2+ ion, it was 1.00 volts. And for the iron 3+ ion, it was 0.77 volts. So, order of oxidizing ability is code for most likely to be reduced, which you've already learned is most positive reduction potential, and that was a reduction potential table, is the most likely to be reduced. So if you want them in order of oxidizing ability, then here you go. Most likely to be oxidized, or cause oxidation, be the oxidizing ability, would be Ce4+, and the next would be VO2+, and the next would be Fe3+. All right, so let's wrap this up. We're just going to talk about some applications of electrolytic cells. Occasionally there are multiple choice questions that are asked in what we call descriptive chemistry, and that's where this may come in handy for you. But primarily, we're just trying to get some loose ends tied up. I think it's always nice for you to understand the relevancy, how the chemistry that we learn applies to real life, applies to industry, applies to people having jobs and being able to earn a living. So here are some applications of electrolytic cells. We already talked about the fact that if you want a pure metal, it's going to be formed from mined ores. So we go out in the miners, dig up the ores go back to a processing plant, and so some of the things that are important in this process would be aluminum. We use aluminum for an awful lot of things, and the Hall-Héroult, I think is how you say that, process is an important one. We also separate sodium and chlorine because we have big salt flats in this country, so we can go to the salt flats and we can dig up the salt out of the ground and use what's called a Downs cell. Again, that's named after the gentleman who figured out this process. And we can purify sodium metal and chlorine gas. Chlorine gas is a huge industry because all of the municipal water supplies work off of chlorine as a disinfectant to kill bacteria in our water supplies. Purifying copper for wiring. We use copper for a lot of things, not just decorative things. We use copper wires in all kinds of stuff. And so that's a big thing. So I won't bore you with the details of all of these things. You can analyze these pictures for yourself. But this one is the down cell, and this one is for the processing of aluminum. And you can see that we use electrolysis for both. Chlorine gas is what we really want to collect from here, and the aluminum itself is what we want to actually collect from this one over here. So it's the molten aluminum that we're interested in letting solidify. Electroplating is a big industry as well, where we apply a thin layer of an expensive metal to a less expensive one so that it's pretty and shiny and doesn't corrode and doesn't tarnish or oxidize. So we've already talked about 14-karat gold-plated jewelry and chromium being plated onto bumpers and mirrors and running boards and decorative pieces on automobiles, to name a few. Charging a battery. We use electrolysis to charge your battery. You have an alternator in your car that is connected to a fan belt, an alternator belt, that is its own private little mechanical generator. When your crankshaft and your wheels turn, your crankshaft turns, your crankshaft is attached by a bunch of different gizmos to this alternator, which constantly recharges your battery. And you know that batteries do eventually reach equilibrium or go dead, as you might say, but those batteries we expect to work for us for a very long time. A car battery usually lasts somewhere between 5 and 6 years, as long as you maintain it and it's not exposed to ridiculous heat and ridiculous cold, which happens in some parts of our country. Corrosion. Corrosion costs money. Lots and lots of money. It's never a good idea for a skyscraper to corrode. So corrosion is the process of returning metals to their natural state, which would be the ores. And that's not good if you've taken a lot of effort to make some of those ores blend into an alloy like steel to build buildings from. So corrosion involves the oxidation of the metal, which causes it to lose its structural integrity and its attractiveness. The main component of steel is iron. So corrosion is all about returning iron to its natural state and taking it out of steel, which is what causes steel to lose its structural integrity. Steel is an alloy. An alloy is a blending of metals. So 20% of the iron and steel produced annually is used to replace this rusted metal that's taking place. So most metals develop a thin oxide coating to protect them. So if it's copper, we often refer to the patina, which is that green coating that you see on the Statue of Liberty, because underneath all of that, oxidation being a big word, all of these fall under the big umbrella term of oxidation. Oxidation. Can't spell. Can't write either. Oxidation. Tarnish is what we usually refer to when we talk about silver, and rust is what we refer to as the oxidation of iron. So these are all terms that you've heard before in just general language. My punishment when I was a child, when I was a bad girl, was to have to polish lots and lots of silver tea sets that my mother owned. Could take all afternoon on a Saturday. I learned not to get in trouble. So corrosion of iron, let's talk about that one a little more, since that one does have industrial proportions and industrial significance in this country in particular. It is an electrochemical process. Steel has a non-uniform surface, since it is an alloy, which is like a solution of metals, if you prefer, a solution of solids. The surface is not completely homogeneous, so physical strains and leave stress points in the metal, as well as causing iron to be more easily oxidized, and oxidation, anox, occurs in the anodic regions of this piece of steel than it is in the other regions, which would be cathodic. In the anodic region, the iron atoms are going to oxidize into the iron ions, Fe2 plus first, liberating 2 electrons. If it keeps going, we'll eventually get to Fe3 plus, and these electrons are released. The electrons that are released are going to flow through the steel to a cathodic region where they react with the oxygen in the air. So the oxygen in the air, along with the fact that we have humidity in the air, so we have some water vapor available, is going to actually make hydroxide ions. So the iron 2 ions travel to the cathodic regions through the moisture on the surface of the steel, think humidity, just like ions travel through a salt bridge. And another reaction occurs in the cathodic region. which is given below. So again, this is not something you need to know about, a little bit about corrosion just because you're a citizen, not particularly because you're a chemistry student. Not a lot of questions on this on the AP exam, but I'm just, again, trying to give you a full education here. Now, what also can happen has to do with a lot of our water vessels, because lots of humidity if the ship is sitting in the ocean, don't you figure? So this means that rust often forms at sites that are remote from those where the iron is dissolved to form pits in the steel. And all of these things are structural defects that can cause big disasters. So hydration of iron, which is surrounding by water of iron, water surrounding iron, affects the color of the rust. So it can be black to yellow to that familiar reddish-brown rust color that we always talk about. If you want to prevent this, a good coat of paint helps. If you coat the metal with the zinc, which is what we call galvanizing. It's hard to buy nails in the hardware store anymore that are not galvanized. If you're going to build an outdoor structure like a pretty deck outdoors for enjoying in the summer, you have to use galvanized nails or your deck is only going to last a couple of years because all the nails holding it together are going to start to crumble. So galvanizing is coating with zinc. This provides, and you can also use cathodic protection, which is to insert an active metal like magnesium, let's say, connected by a wire to the tank or pipeline that you're trying to protect. Magnesium is a better reducing agent, therefore more easily oxidized, than iron. And the magnesium anode dissolves and has to be replaced from time to time, but it protects the steel in the meantime. So it's just a good example of a steel tank buried underground. A lot of septic tanks, which are non-urban, more countrified sewage systems, which are ever so important to your quality of life, they work this way. And then ship hulls, which are also big giant chunks of steel, often have bars of titanium that are attached to them, because in salt water, titanium acts as the anode and is oxidized instead of the steel hull. So it's much cheaper to keep replacing your titanium bars than it is to replace the entire hull of a ship. So thank you for your kind attention. That is now the conclusion of all that is electrochemistry, with this piece right here being the most important piece of what you're going to utilize in the second half of the unit. And galvanic voltaic cells, like I told you earlier, takes up about 2/3 of the time in this unit, but don't neglect this concept. There will be 2 recordings that you should look at. One of AP problems, which you may have already viewed for galvanic voltaic cells from the worksheet that your teachers have from the NIMSY teacher website. The other is the second part of that worksheet, which involves electrolytic problems. So hope you found this helpful, and I hope you do really well on this unit exam. I wish you the best. Thanks so much.